let's compare series using the direct comparison test. And what are we comparing? Well, we're trying to see which series is larger and which one is smaller. You'll see where this is going in a minute. So we're going to have two series. One of them is called A, one's called B, and this is the explicit form of each of them. And B is going to be consistently larger than or equal to A, all right, for all the values of n. So let's move forward. If I have some series that is the large series and it converges, and that means that I am able to determine that it does not approach infinity, right? If the big series doesn't approach infinity, then the smaller series definitely doesn't, okay? Again, B's the big one, A's the smaller one. So if the big one converges to a specific value, then the smaller one must also converge, all right? Similarly, if the small one diverges, the small one blows up, like it goes towards infinity, the series goes towards infinity, then the one that's bigger than that is definitely going to go towards infinity. Okay? So here we go. If I have a large series that converges, then the small series must also converge. So the way I've drawn it in the past is like this. Let me grab a scrap piece of paper. If I have some series, and I'm going to represent it in a way that they're generally not represented. And I'm going to have a series that's going to be, we're going to say that this one is B sub n, it's going to be purple, and we're going to have A sub n, and it's going to be red. And we're going to do this. We're going to let that be A, and that was the next series, next dot, next dot, next dot, next dot. I don't want you to confuse this with an integral, but basically I want to add together this length plus this length, 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 plus this length for forever, for all of time, right? And it's just going to keep doing its thing, right? And B is going to be bigger than that, so it's going to do this, and it's going to go all the way down. It's going to be all that right there. And it's going to be this one as well. Whoops. I meant for them to be just pretty much side by side, but it's the same idea. Practically simultaneous, that's what I was going for. And B is larger. Didn't mean for it to be that much larger. There we go. There we go. You get my drift. But B is going to be larger than A. If I know that A approaches infinity as I add all these red marks up, if A approaches infinity, then if it diverges, then B has no choice but to diverge because it's even bigger, right? Okay? If I said that B converges, we start this whole process over and I still have series that might be represented in some way vaguely like this, and I say, oh, well, B converges. I add this purple line plus this purple line, this length, this length, this length, all the way to infinity, and somehow with this pattern that continues, this is going to converge. Well, then I'm able to nail this down to be a specific number. Then I know that this red one definitely is because it's smaller. That's the idea. So what we're going to do is find a series of known convergence and compare them. So bear with me. Here we go. Determine the convergence or divergence of this little guy right here. So this little guy right here looks a lot like this. And I'm going to write this one out kind of in sentence form. We're going to compare to the sum from 1 to infinity of 1 over 2 to the n. Okay, they look a lot alike. We're just adding a 4 in the denominator of the one that they gave us, right? We're going to compare it to this, which, all right, pause that thought. We're about to finish this sentence talking about this one, whether it converges or diverges. And then we're going to start making some comparisons. Okay, well, this one might converge, it might diverge, and which one's bigger, which one's smaller. And then we're going to start digging through all this stuff and figure out, I could nail down what this one does. I may not know the exact total, but I could say, oh, this one converges or diverges because I can talk about that one. Okay, this, based on our knowledge so far, is this a P-series? Pause, think. No. Is it geometric? Yes. So which is geometric? And, okay, now that we know it's geometric, let's talk about what R is. R is, well, you could rewrite this as 1 over 2. Let's grab a scrap piece of paper yet again. We could rewrite this as 1/2 to the n. It'd be the same thing, right? Therefore, we could say that r is a half. Because r is a half, it's between -1 and 1. Ooh, lots of ands in there. All right, now it's grammatical. Here we go. Compare this to that series, which is geometric, and r equals -1. Let's just change that last and to be which. Which converges. Okay, now we have compared this to a series of known convergence. Now we could find what it converges to because it's geometric. We have a formula for that one, but let's not play that game. That's not important. Final answer for this is going to be yes, this converges, or no, it diverges. But now we're going to have to play with the idea that this converges. So if this series converges, let's see. I need to decide which one's bigger. So let's kind of tinker with this idea. I'm going to switch colors for just a second. We're going to go blue. And I'm going to write the series they gave us. And I'm also going to write the series that we made up that we think looks a lot like it. And now we're going to put a symbol in between. For all values of n, which one's bigger? Okay, so if I plug in a 1, I'd have 1/2 here. I'd have 1/6 here. That one's bigger. Okay, plug in a 2, plug in a 2. That one's bigger. This denominator is going to be consistently bigger, which means the bigger denominator makes it a smaller fraction. Here's what that means. Because, here we go. We have decided which one's bigger. Therefore, based on what we have up here, a sub n, that's A, that's B, and because the one we made up that looks a lot like it converges, then the smaller one must also converge. Barely had to do any math whatsoever. Which converges. Since 1/4 plus 2 to the n is less than or equal to, but never actually equal in this case, 1/2 to the n for all n, for all n's that truly matter, particularly, because, you know, like 1 to infinity. This series that they gave us also converges. The one we picked was consistently bigger, and it converged, so the smaller one also converged.